Hi everyone, welcome to our lecture about clients. We are talking about network communication, network interprocess communication, and today's lecture focuses on the client end of that transaction. Alright, so let's jump right into Berkeley sockets. So Berkeley sockets is the de facto network communication method that's used across networks, across local area networks, across the internet. It was developed back in the early 80s for BSD Unix, and it was part of a grant from DARPA. So originally, through a defense agency research budget, is the development of these sockets. So there are other ways to do it other than sockets, but really this is the only way that's used out there. You'd have to rewrite your entire own version of TCP for some other network protocol that you wanted to use. It's just not worth it. Just use sockets. So a way to picture these things is to think of your processes as having a socket as an endpoint. And it's an endpoint of communication between two processes. So the network exists and it connects together the two sockets. The API that you use to manipulate these sockets with is going to treat the network connections like files as much as possible. And knowing Unix, it's pretty possible that they'll be able to make these things look like files in just about every way. So the old file descriptor table that we've looked at, where 0, 1, and 2 are going to stand for standard in, standard out, and standard error, as we use the socket call to open up these sockets, they'll be entered into the table in the same way that calls to open adds things to it. So our file descriptors will go from 0 to 1 and 2 for the 3 built-ins, and then 3, 4, 5. Those could either be files that were opened with open, or they could be sockets that are opened with the socket call. When we have multiple processes that are all communicating with each other, including multiple processes on our own computer that need to communicate, we have a limitation of addressing. An IP address can only identify the interface on the computer, so the actual network jack that's there, not the process, not a particular process. So how do we know which process is communicating at that particular interface's IP address? So here's our computer with its IP address, but it's got all these processes. So which of these processes is sending data out from that address? And if anybody is sending data to this address, how do we know which process it needs to go to? That is where ports enter. Imagine that we've got a house here, and the house number is 31 on this house, and we can assign a number, a unique identifier, to each one of the portals into the house. So maybe this one is port 6, and this one's port 1, and this little window up here is port 9. So the individual ports tell us the entrance into that house, and there could be each one is different, each one is a different process, a different person listening at each individual entry. So the ports are used to reach a specific process on the machine at a given IP address. So a complete address is going to be something like 43.144.31.223 at port 80. So note that the colon here separates the IP address from the port. So for the documentation for sockets, most of the related calls are going to be in the 3N section. Here's a couple of calls to help find sockets. All the information to use these things, to use the network API, to use the library, is kind of spread across a lot of different places. So it's definitely recommended that you're going to start from a known good network program. These things are difficult to write. The low-level function calls that we're using are difficult to write from scratch. So start with the code that I'm going to give you, which we'll talk about here at the end of this particular lecture for the client side. And for the next lecture, which is about servers, follow the code included on that one as well for the server code. So you'll start from a known good place. So here is the process we're going to use to make these connections. Step 1 is going to be create the socket endpoint with socket. So you're going to instantiate the socket with this socket call. Then we're going to connect the socket to the server on the other end with a connect call. After that's done, we can use read and write, or send and receive, which are the more network-oriented versions of read and write, to transfer data to and from the socket that we just created. So you send data to the socket, and then the network API below your application level, so all the libraries that are involved there, will send automatically that data to the socket on the other end. So all you do is write data to the socket, and it's sent automatically through the network to the other side. So sockets are going to act like files. You can read and write to them They're bidirectional, so you can use both read and write at the same time on this. Well, you can use them both on the same socket, iteratively, so one and then the other to read and write. So they're both, so send and receive are specialized versions of read and write. They have some special flags that you can use to make them behave a little bit better, but you can also just use read and write. So here is a demonstration of the socket call. So the different parameters here. So it's going to return the file descriptor if it succeeds. So remember that this thing inserts entries into the file descriptor table just like open does. So we get a file descriptor out of it when it succeeds. The domain parameter here can either use AF INET or AF Unix. I haven't had much luck with AF Unix. That builds a small, a lightweight socket. It doesn't have near the capabilities of the full AF INET one. So I just use AF INET to get a full-size socket, and it'll work. So for type, this is where you specify whether it is TCP or UDP. So sock stream for TCP and sock dgram for UDP. The protocol variant here, you can specify different versions of TCP, but just use 0 for the normal one. Down here is an example of the actual call all put together. Note that we've got error checking in place for if a -1 happens to say something has happened and go ahead and exit. Here's the connect call. We have the sockfd parameter right as the argument as the first parameter, which is the socket that we've previously created that we now want to connect to a socket on the other end. So sockfd is where we put our socket we just made. The next one is a structure, the address to a struct of type sockaddr, and that's just going to hold the address of where you're connecting plus some other settings. And it's a little funky, so we'll talk about how it works. And then finally, the size is the size of the address struct that you just passed in. And -1 is returned if the whole thing doesn't work. So here's an example of the connect call. Note here's socketfd that we put in. Here is the server address variable that we've pre-created and we're passing in the address to it. Note there's a funny cast here, where even though it expects of type struct sockaddr as a pointer, note that we're casting it to that, which implies that this is not of that type. So we'll look at that on the next few slides. And then note here is the error exit if something happens. Something bad happens. Okay, so on this one, we're going to demonstrate what happens with the how we get the actual address. And first, note that the location, this server address variable that we're going to store this all in, is of type sockaddr_in. Server address is the same name as we used on the previous slide. Here is server address that's used, and the type that's expected by connect is sockaddr of a struct. But see that is not at all what we have. We have sockaddr in. And the reason for that is because there's actually a lot of different structures that can be used to hold the information. And when we finally have the one created that we want to use for the connect call, you then cast it to what connect expects, which is kind of a master version of all these different network structs that could have been used. And if C was an object-oriented programming language or supported the full inheritance that something like C++ does, we could have used class inheritance to solve this problem. But instead, since it's C, we cast it in. Okay, so to load up this server address struct, there are 3 different members that we're going to care about for this for here. So first, the family again is AFINET. The port is going to be 7000 in this case, just a port that I picked. But we have to use the HTONS function in order to convert this into the type of format that the SIN port is looking for. So what HTONS does is it's the host to network short. So short being a short integer, and the host to network refers to the fact that the PC byte order is least significant byte first, whereas the network byte order is most significant byte first. So this 7000 that you're going to type in is typed in the way that the PC is expecting that number to be represented. But the network expects it in the opposite order, so the least significant byte is first in order. So HTONS essentially reverses the order of the bytes and stores those into import. This is a bit of an infuriating hack that has to happen, but without it, the ports can't be understood by the networking infrastructure. Then for this inaddr member of the server address struct that we're using here, there's a field of that called saddr, and you can use this inetaddr function and pass the actual IP address in the standard dotted notation format. And that this function, inetAddr, will convert that into the integer that this structure requires. So a lot of setup, but using this code here lets you just put the values in and get the results you want. Okay, so now let's go ahead and fill out the address struct that we're going to need. So for this one, here's our sock_attr_in structure, and here's a host entity structure that we're going to use to hold the information of our target. So our target is specified by here, www.oregonstate.edu. We're going to do a DNS lookup of that domain name with the older function getHostByName, and that will return the information we need into server host info, which is hostEnt, of type hostEnt. Now getHostByName is a bit of an older function, but it's certainly good enough for our purposes here. For anything more complicated, you'd use one of the more modern functions, but this works for us, especially since we're going to be using localhost for the most part as our target. So test server host info for success, make sure it actually recorded what we wanted, or received the data we wanted. And then we're going to load up our server address struct. So the family is AFINet, our port is port 80, which probably means we're connecting to a web port here. And to preserve the address information that we retrieved with getHostByName, we have to memcopy it in. So this is going to preserve the special arrangement of the bytes in these variables by just doing it as a byte-by-byte copy, regardless of the format or the storage or the structure of the bytes that are there. So the first argument, the first parameter of memcopy is going to be where you're copying to. And the second parameter is where you're copying from, which is going to be from our host info. And the last one is how much we're copying. Now let's go ahead and send. Once we had a connection that had been established with the connect function call, we can send. So here is our send function. We give it the socket file descriptor that we've already created, a message that we've previously created, and here is the size in the number of bytes that we're going to send. And then the flags is for configuration at the end. You can leave that as 0 if we're not using any. It's going to return the number of bytes that it actually successfully sends. So imagine we have some message that we've created and we set it to some value, and then we just send it like this with the send call. Here is socket FD, here's the message, 1024 is the size that we're going to send. So here we're assuming that message has been completely filled with bytes that we're going to send. R is the result of what we sent. And if R is anything less than 1024, then there may have been an error. And if this happens, then just put a loop around send and send again what didn't get sent previously. So if it sends 1,000 bytes, you need to send the last 24 again. Okay, so send is going to block until all the data has been sent. That happens. There's a couple other things that can cause that to not actually send. So if the connection goes away, or if the signal handler gets interrupted. But for the most part, you can rely on sending all the data at once. Since internet connections can fail all the time, so maybe the internet dies, maybe the network goes down, maybe the client disconnects, some signal handler blows away the connection or pauses it or interrupts it, and your program crashes. Whatever it is, because of this, you need to have a system in place to deal with the fact that you did not successfully write all the data. So Cliff Stoll was a man who wrote a book called The Cuckoo's Egg, and The Cuckoo's Egg is about a computer hacker breaking into a set of computers. And in order to keep the hacker online while they trace the call, Cliff uses a set of keys, and he jangles it over the top of the bare connection wires in order to add interference to the line and slow the connection down. And it worked. It's a great story, and I highly recommend this book. It's a true story, so I think you'll enjoy it quite a bit. To receive that data, we are going to use the receive call. So receive takes a socket file descriptor, and then the buffer for where it's going to be putting the data into, the maximum number of bytes that it's receiving, some configuration flags at the end. So here's some sample code that does that. We have some char buffer that we have memset. Then we receive right into it. Note the socket at the front, the buffer we're putting it into, how big the buffer is, -1, with no special flags. And the reason why we -1 off of what we stuff into it is because we want to guarantee that we're leaving a null terminator at the end of the buffer, so that if we ever write this thing back out, so to the screen or to a file, that we know it's going to end at some reasonable time at the end of the buffer. So if what we've received is less than the size of the buffer, since I requested everything, I requested that we fill up the buffer -1. If I get less than that, we may have some sort of error. So there might be more data. You might need to call receive again. You don't know, but the only thing you do know is you did not receive everything that you requested. Was that because you requested too much? Was it because there wasn't enough there that you requested? That's up to you and the protocol that you're putting in place, that you are how you are managing the amount of data that you're sending at any one time. So data can arrive in odd-sized bundles. So receive or read is going to return exactly the amount of data that's already arrived. It will also block if the connection is open but no data is available. So you have to be careful to match what you send with what you receive. So otherwise you're going to have these erroneous read or write calls that will block when there's no data that can be sent, or if there's no matching read call on the other end. So be careful to match what you send with what you receive. There's this function control function that'll let you set non-block on a socket. But if you're doing that, that means that you'd have to be pulling a socket, P-O-L-L-I-N-G, pulling the socket periodically to see if there's data in there, which is a computationally intensive process. There's a better function for that, which was invented just to solve this problem, and it's called select, and we'll talk about that in our next lecture. Okay, so to use the control codes, this is something that we talked about in a few lectures ago, where we talked about scanning for something in the text that lets us know we've reached the end. In this case, this is the same code as we had before, but we're looking for the double @ symbol. And if you remember, that double @ symbol is what we were using to indicate that that is the end of the data we're trying to send. This particular loop looks for that, receives data, and then tests to see if what we needed, if that the actual symbol is inside the string that was retrieved. Concatenates everything together and then outputs it to the user at the end. So we've talked about this once before, but it's worth bringing up again in the context of understanding what you actually receive, so and what you're trying to send. Let's help verify the contents of the buffers. So since a character can be represented as both an integer and a character, and knowing that the character form can be difficult to display on the screen, we can output characters as integers. So this block of code here is going to show all characters up to the first new line. So it loops through a particular buffer, and it goes from 0 to the string length of this buffer to show us the contents of what it is. So the one down here is going to go from the beginning of the buffer through the entire size of it by using size of. That will show all the characters in the entire array. Here's what the output, say, might look like. So we can tell the difference between lowercase o, uppercase O, and a 0. They readily show up as different integers. We can see spaces and new lines and tell the difference. And also between the null terminator, which of course is 0. We can tell the difference between the lowercase l, the uppercase L, and the 1. They all show up as separate integers. So you'll use an ASCII table to actually tell what these numbers are if you didn't have the character representation there with you. Okay, so let's look at the actual code that we are going to be using. Here is client.c, this is page 1 of 2, and there's a matching server code called server.c in the next lecture. Now, these two programs are designed to link together. So the send and receive calls are paired up so that they don't block or stall unnecessarily. So note that you can't just use this as it is as a generic server. You're going to have to adapt the code. This shows you code being or data being sent back and forth. Here's all the includes that we'll need up at the top of the program. Here's an error function that we'll use in a few different places. It simply prints out the error and then exits if we use it. Here's all the various integers and structures that we'll need, and the buffer that we'll use for sending and receiving. This is a usage call. It's going to test to make sure that we've got all the arguments that we want. And in this case, our usage is the name of our program, the host name. So that's going to be, client, or local host, something like that, and then the port. A host name could be an IP address, that kind of thing. So set up the server address struct is going to be our first task. First, we'll use memset to clear out the address struct. We'll use atoi to convert the integer from the string that was given by the user, stuff that into our port number. set the INET and set the family and the port into our server address struct using the functions and flags that we know about. Use the getHostByName function to convert this argument from the user into the actual target that we're going to. Then do some error checking. If everything came out okay, then load up that address into our server address struct. Now that that's all done, we can use socket. So socket here is going to just create the socket. So this is going to be a TCP socket using a standard full-bore INET socket. Error check if any results happen, then connect to the server. So here we take our socket, we cast the struct that we are storing our address into as our second parameter, pass in the size of it, and use the connect function to connect this thing out to the server. This makes the connection to the server and verifies that it's there. It returns an error if something happens. Then let's get an input message from the user. So print out to the user that we are going to request something from the user. We're going to memset out our buffer to make sure it's empty and clean and ready to go. We'll use fgets to get something from the user. Note that we are leaving a null terminator at the end of this thing. Then we are going to remove the trailing new line that fgets is going to add in. This is using this kind of fancy function, string CSPN, which is going to locate where that new line is and replace it with a null terminator. Then we're going to send a message to the server. So we use the send call with the socket, the buffer that we've preloaded, and the length of that buffer. So that string length is going to tell us at the null terminator, wherever it occurs inside there, where to stop. Then we are going to use error to error check, and then we are going to verify that string length has actually showing us that all of the characters were written, and then we'll get the return message from the server. So here we're going to memset our buffer, then we're going to receive back from the server. So now that it's empty, we can receive. So again, we leave a null terminator at the end to make sure it's clear. Then for the characters that are read, we are going to verify that the number that we received is either 0 or greater. Otherwise, there was a total error with reading from the socket. Print it out to the client to show what we actually received. Then close the entire thing down. The results on this thing are that we can compile our client, compile the server, which we haven't looked at yet, start up the server in the background at a particular port, start up our client targeting localhost, which is our current computer, at the same port, and then run. So the client says enter text to send to the server. So we enter it in, hit enter. The server says I received this from the client, and then the server says I got this back from the server. I am the server and I got your message, and then everything terminates. This is the server shutting down. So that shows us a successful client connection and sending data back and forth. In our next lecture, we'll look at the server connection, receiving and sending data back. Well, I hope this will get you going. Please use this code for the assignment in this course, and as a great starting point for getting started with network code here. Thanks, and we'll see you next time.